Okay, good morning. So today we will talk about the last topic of this course, and this will be algebraic varieties and ideals. So let's start with some discussion on algebra versus geometry.
Wait, if this is the last topic of the course, what are the two topics scheduled for next week?
So the next week is the RR week. There will be no lectures during the RR week, only office hours.
Sorry, I misread the calendar. Thank you.
So this week is the last week of instruction. So yeah. So let's start some discussion on algebra versus geometry, and kind of the main question is whether we can study geometry purely in algebraic terms. So can we study geometry purely in algebraic terms? And it turns out that many questions in many geometrical questions can be translated to the algebra language. And for example, in geometry, there is one of the most important notions is a point. So is there any way to think about the point in algebraic terms? And let me give you an illustration. So recall that for any set X, let X be a set and F be a field, then we can define the ring of functions. The ring of functions on X is defined as follows. So as the set of all functions, from X to F. And recall that for a point, P in X, or a point P in X, we can associate an ideal, ideal I sub P, which consists precisely of all functions which are zero at this point P. F of P equals to 0. Well, now the claim is that this ideal is actually maximal. Claim IP in F is a maximal ideal. Well, ideal. And the proof would go as follows. So let's, for the sake of contradiction, suppose that there exists, well, actually, we can even just suppose there exists an ideal which is strictly greater than IP. So suppose IP is strictly included in J, which is also an ideal over ring F. Well, and then take any function g of x which belongs to j minus IP. So it's a function which is in j but not in IP. Well, by definition, we know that the value of this g of p at the point, the value of this g at the point p is not zero. And now we claim that then this g together with IP must generate the entire ring F. Okay, so now let f of x be any function in this calligraphic F. Then the following difference. So let's consider the function h of x, which is defined as f of x minus f of p divided by g of p times g of x, right? So because g of p is not zero element of a field, it is invertible. So the thing here is a well-defined constant. So the thing, this is a well-defined constant, right? And this is the function which must be in IP. That's because, let me erase this. So this guy belongs to F, belongs to a field F. This guy belongs to this guy. Well, note that h of p equals to 0. So h of x is in IP. Okay. But then what do we have? Then what do we have? So this f of x. So let's use now let's express f of x through h of x and g of x. So this is h of x plus f of p divided by g of p times g of x Okay, so this thing here belongs to ideal j, right? Now this thing here also belongs to ideal j, because this is just some constant function multiplied by the function in the ideal j. So that's in j. And of this, you can think that this is just a constant function. And the product must be still in the ideal. So this entire thing must belong to an ideal j. What we just proved, that every function in F belongs to an ideal j. So we have proved that j must be equal to F. Well, because this is valid for any ideal j strictly larger than IP, because this is valid for any ideal j strictly larger than IP, we conclude that IP is maximal. IP is maximal. Okay, so now we have the question whether we can think of points as maximal ideals. question. Think of points as maximal ideals. Well, let me say immediately that the answer is not always, but in many important special cases. Yes, in many important special cases. In fact, we can translate most of the questions from geometry to the pure algebra level. So we can study geometry in terms of algebra. So we can study geometry, put it in quotes, in terms of algebra of certain subring of a ring of functions. And examples will include so this gives this is actually a rather powerful idea which used in many different areas of mathematics. And examples include algebraic geometry, where this X is just the set of n tuples of a field. So if, for example, this F is a field of complex numbers, right, this will be an n-dimensional complex space. And this ring of functions, instead of considering the full ring of functions, one considers the polynomial functions in n variable. Polynomial functions on X. Well, another kind of neat topic is topology. So topology. So when X is a topological space, the so-called topological space, then one can look at the ring of continuous R-valued functions. So let's look at CXR, continuous real valued functions. And this algebra can tell us a lot about the underlying topological space. Okay, so today we will talk about this part. Talk about today. And this thing is neat, but beyond the scope of the course. Neat, but beyond the scope of 113. So just can't help mentioning this, that in fact, if you know the algebra of continuous real-valued functions on compact Hausdorff space, then this algebra uniquely determines the space. So if the algebras are isomorphic for such spaces, then the underlying topological spaces must be homeomorphic. So in a sense, algebra knows everything about such space. Okay, but today we will stick with a simpler example, which is a little bit older, of the algebra of polynomial functions on n-dimensional space. Okay, let's talk about algebraic varieties and ideals. Varieties and ideals. Okay, so again, let for now X be the space of n tuples of a field F, be the set of n tuples of elements of F, and of a field F, and we will denote elements of this set X as vectors. Note A with overline to be the n tuples of elements there in Fn. Okay, so with this space we can associate a polynomial ring of polynomials f in n variables, x1 to xn, and for short we will simply say that this is f of x overline. And variables. Okay, so each polynomial defines an f-valued function on x. So each polynomial defines an f-valued function on x. Well, because for every a bar in Fn, we have an evaluation homomorphism. F evaluation homomorphism. F with a lower script, with a A overline. Now it's homomorphism from the polynomial ring to F. Okay, and our first definition will be of an algebraic variety. So definition 1. So let S be a finite collection of polynomials. Be a finite subset of our polynomial ring, f of x bar. Then the set of all common zeros of this n polynomials, the set of its set of common zeros V of S. So that's precisely the set of all elements in Fn, such that F1 when evaluated at A equals to F2 when evaluated at A equals all the way to Fn evaluated at A equals to 0. And this set is called an algebraic variety. It's called an algebraic variety. So this is a very special subset of this n-dimensional space, which can be described as the set of common zeros of finitely many polynomials. Okay, then, and immediately what we can do, we can associate with every algebraic variety. In fact, we can associate ideals. And with this subset of polynomials, we can associate ideals generated by this n polynomials. The point is, if f1 and f2 are 0 on this V of S, this means that any possible kind of algebraic expression you can construct in f1 and f2, you can multiply them out, add as you want, it still will be 0 at all points of V of S. So this motivates the following lemma. Lemma 1. So let kind of G be any polynomial in the ideal generated by f1 to fn. Be any polynomial in the ideal generated by S. Generated by S. Then what can we say? That G vanishes on V of S. And G vanishes on algebraic variety V of S. In other words, if we look at G of A, it must be 0 for all A in V of S. Sorry, that's a mess here. For all A in V of S. Okay, now the proof is quite simple. So note that 2 lectures ago, we have proved that if G is in the ideal, then it must be, it can be presented as the following expression. So we can say that this is f1 of x, 1 of x times r1 of x plus f2 of x by the r2 of x, etc., all the way to fn of x multiplied by rn of x. For some r1 of x, rn of x being in our polynomial ring, being in f of x. Well, then if we evaluate this expression at A, what do we get? G of A equals to f1 of A, r1 of A, all the way to fn of A times Rn of A. Okay, so this guy is 0, and then it doesn't really matter what is the value of a polynomial R1 when it is evaluated A. This guy is 0, so the whole thing actually equals to 0. Here we go. Okay, well, an immediate corollary of this lemma would be the following, that if we have two ideals, so if we have two finite subsets, if S1, S2 are subsets of f of x, sorry, S2, if S1 is a subset of f of x and S2 is a subset of f of x such that the corresponding ideals are the same, well, then necessarily the associated algebraic varieties are the same. So the sets of all common zeros of polynomials in S1 and S2, they coincide. Well, proof indeed kind of for every f belongs to S1, we have f belongs to an ideal generated by S2, and from here it follows that f of A equals 0 for all A in V of S2. Similarly, well, as a corollary, the set of zeros of S2 is a subset of zeros of S1. Well, the opposite inclusion is proved in the same way. That inclusion is proved in the same way. Okay. So different subsets can define one and the same algebraic variety. And in fact, you're all familiar with that, right? You're all familiar with that. So suppose you're looking for the set of common zeros of two polynomials, 3x squared minus y plus z, and x squared plus y. Right? So this is equivalent to a set of solutions to the following system, right? Then what you know is that if you kind of add the second equation, if you subtract add the second equation to the first one, then the set of zeros will be the same. Okay, so actually here, what do you get? So 3x squared. So we can get rid of, for example, of x squared in the first equation using that, right? Just by subtracting 3 times the second equation, and that will be minus 4y plus z equals 0, and x squared plus y equals 0. Okay, so that's when you, for example, are solving systems of algebraic equations. That's precisely what you're doing. You're changing the generating set for the corresponding ideal. And that's okay. So now can different ideals correspond to one algebraic variety? Well, the answer is yes. And the example 2 here would be the following. So let's say that x equals to R2, two-dimensional Euclidean space, and let's look at the following. So let's look at S1, which will consist of a polynomial x, say x1, and S2 will consist of the polynomial x1 squared. Now then, if you look at the associated algebraic varieties, what do you find? So this is x1, this is x2, right? Now the set of all common zeros will be precisely when x1 equals 0. This guy. And this is v of s1 equals to v of s2. But it's not that bad, in fact. Remark. However, for the case when our field is just complex numbers, there is a one-to-one correspondence between algebraic varieties and radical ideals. Radical ideals. So if you already solved the problem B from the recent homework, you know what the radical ideal is, and that's precisely the collection. It's precisely the ideal which is equal to its own radical. And if you look only at the radical ideals, then they will correspond to algebraic varieties. Okay, we're not going to, of course, go into details about the proof of that today. Okay. Now let's look at the following. So we already kind of talked that the maximal ideals would correspond to points. The radical ideals would correspond to algebraic varieties, which are very special subsets of this n-dimensional space. And let's see what happens when we have an inclusion of, so let's say that we have an ideal generated by set S1, and it's inside the ideal generated by S2. And f of x. And what can we say is that the set of zeros of S1, the set of zeros of common zeros of S1 includes the set of zeros of S2. And the proof is similar to lemma 1. You just need to take 1/2 of that proof. And this brings us, okay, so kind of the inclusion between different algebraic sets also corresponds to opposite inclusion of the corresponding ideals. And here it brings us to the main point. So key idea, that structure of ideals, structure of ideals in the polynomial ring, f of x, I use double line here, can tell us a lot, about solutions to polynomial equations, about sets of solutions of polynomial equations. Okay, and in fact, in the polynomial, in the ring f of x, all ideals are generated by finitely many polynomials. And this is the so-called Hilbert basis theorem. Theorem 1. Hilbert basis theorem. And it is formulated as follows, that every ideal in the polynomial ring f of x is finitely generated. Finitely generated. In other words, this ideal is simply generated by polynomials, let's say f1 to fn, for some finite collection of polynomials. Well, let me just give you a sketch of the proof. So let me put a remark here. First remark. Well, when when our space X is just a field, and we look at the polynomials over a field, X equals f to the 1. Forgetting to switch the color of the marker. When X equals f1, and we know that all ideals are principal, meaning they generated by a single element. When X equals to f2, this is no longer true. But one can always find finitely many polynomials. Can always find finitely many polynomials. It can be much more than 2, of course, even in the two-dimensional space, but still every ideal in the polynomial ring in many variables is finitely generated. Okay, let me say a few words about the proof. Sketch of the proof. Since we already talked about Noetherian rings, I can really explain how the proof goes. So recall that last time we have stated theorem that f of x is Noetherian. In other words, it satisfies the so-called ascending chain condition that for every chain of ideals, I0 and I1, etc., there must exist for any infinite chain of ideals every infinite chain of ideals, there must exist n such that in plus 1 equals to in. Equivalently, one can say that there is no infinite strictly ascending chain of ideals. Okay, so now let I so now we're going to prove that this actually implies immediately that every ideal is finitely generated. And now, for the sake of contradiction, assume that I in f of x is an ideal which cannot be generated by finitely many polynomials. Many polynomials. Okay, so we'll construct a sequence, struct chain, strictly ascending chain of ideals, strictly ascending chain of ideals as follows. So let's start just with one polynomial in I, right? Because I is not finitely generated, the ideal generated by f1 cannot be the entire I, right? So we can find another polynomial, f2, which is not in the ideal generated by F1. So we can take a larger ideal. Well, because it's still not not the whole thing, we can take F3, F3, etc., where Fj belongs to I minus the ideal generated by F1 to Fn minus 1. I can always choose such Fj because I is not finitely generated. Well, but look what we just constructed. But star would be an infinite strictly ascending chain of ideals. Strictly ascending. Chain of ideals. So here we come to the contradiction with our initial assumption. So here come to contradiction with our initial assumption. That I is not finitely generated. Okay. So this is basically how the Hilbert basis theorem proved that every ideal in f of x is finitely generated. Okay, so any questions? Any questions so far about this? Okay. So let's talk. So what we, as a summary, what we just proved is that every ideal in the polynomial ring in many variables is finitely generated, and radical ideals, they are in one-to-one correspondence with solutions to algebraic equations. Okay, so this brings two questions. First of all, A, given two finite sets of polynomials, finite subsets, let's say S1, S2 in the polynomial ring, Xn, polynomial ring. Can we produce an algorithm use an algorithm which determines whether the corresponding ideals are the same. Determines whether ideal generated by S1 is the same as an ideal generated by S2. No. And finally, given an ideal, ideal I generated by F1 to Fn. F of x1 to xn. Can we produce an algorithm use an algorithm which determines whether a given polynomial is in this ideal. Determines whether the given polynomial g in this ideal. Well, it turns out that the answer is yes. Answer is yes, and it involves constructing standard generating set for ideal known as Grobner basis. Okay, so first note that kind of B always follows from A. First note that B always follows from A. And that's because this G belongs to an ideal generated by F1 to Fn if and only if the two ideals, namely the generated by F1 to Fn and the generated by F1 to Fn and G coincide, right? And also, secondly, note in the case of polynomials in one variable, also in one variable, well, both questions are solved by division algorithm. Both questions are solved by division algorithm. So let's say a few words about that. So one variable case. F of x1. So let's look at the set S, which consists of finitely many polynomials, F1 to Fn. It's a subset of f of x1. And S2, oh, that will be S1, and S2 will be G2 to, say, GL. And G2, S2 will be G1 to GL. And F of x1. Okay, so all ideals in f of x1 are principal. All ideals in f of x1 our principle. So in fact, an ideal generated by S1 equals to an ideal generated by F0 for some F0 which can be computed using division algorithm. Using division algorithm. And basically take polynomial fj of lowest degree and divide all f1 fn by fj, right? Then what you will get is that the reminders of this division, there will be of degree less than fj. Then out of the result, you take again the polynomial of the lowest degree and you divide all the polynomials there by the polynomial of lowest degree, etc. So you will end up eventually with, because each time either you get all reminders 0, then you're done, you found the generator, or you can continue it by decreasing degree. So this algorithm stops, and this gives you a generator of the ideal. Okay, similarly, S2 is again an ideal generated by same G0, and the two ideals coincide. S1 equals to S2 if and only if this kind of the generator of 0 is just the multiple of generator G0 or some C in F minus 0 or some non-zero constant. So this thing called Euclidean algorithm. Algorithm. Pretty much how you find GCD of integers. An algorithm to compute GCD. Okay, so now we want to kind of have a division algorithm, right? Now we want to have a division algorithm for polynomials in many variables. For polynomials in many variables. Well, but here, here's the puzzle. But here's puzzle. Which term is leading? Which term is leading in, say, polynomial in 3 variables, f of x, y, z, and let's take x squared y plus y squared x plus z cube plus x squared plus y plus 3. Well, when we have a polynomial when we had a polynomial in one variable, it was obvious which term is the leading, right? You just take the highest degree term in this one variable, and you start dividing by eliminating this term, and this is how you do the division algorithm. Okay, so now we have to agree which terms we consider leading, and to this end, we need to have a total order on monomials. Well, and this total order should behave well, which behave well with respect to multiplication of power products. Power products. Okay, so let me explain what does it mean to have to behave well. That will be definition 2. So we say that monomial ordering. Okay, so we say that we have a monomial ordering if we have an operation, let's say less from the set of power products cross power product to true false, so which compares the two power products, satisfying the following conditions, following 4 conditions. Satisfying, so condition 1 is that 1 is less than all power product for all monomials which are not equal to 1. So here, of course, we want to say that kind of 1 is a subleading term to x, and 1 is a subleading term to y squared x, etc. So basically every non-trivial monomial. Now the second condition is that for PQ, for monomials PQ, exactly one of the following is true. Exactly one of the following is true. That either P less than Q or P equal to Q or Q less than P. Well, or let me just Q less than P. Okay. Third condition on the monomial ordering is that it is transitive. It is transitive. In other words, whenever we have that monomial p is less than monomial q and monomial q is less than monomial r, from here it follows that monomial p is less than monomial r. Or less is probably a little bit confusing. Let's say subleading to monomial r. And finally, 4, that it is consistent with multiplication. Consistent with multiplication. That whenever we have monomial p, which is subleading to q, from here it follows that monomial p times r for every monomial r is subleading to monomial q times r. Well, for example, if we say that x is subleading to y squared, from here it follows that x cubed is subleading to y squared x squared. Okay. Well, remark that such orderings do exist. Remark there exist several monomial orderings satisfying conditions 1 to 4. Satisfying conditions 1 to 4. And for example, let's do 2 examples. So let's say example 1. And this is a so-called lexicographic order. And here we would say that kind of the monomial x1 to s1, x2 to s2, all the way to xn to sn is subleading to monomial x1 to t1, x2 to t2, all the way to xn to tn, if and only if and only if si is less than ti for the first si not equal to ti. Okay, so for polynomials in 2 variables, this means that 1 is subleading to y, is subleading to y squared, is subleading to y cubed, etc. And all powers of y altogether, no matter how large, are subleading to x. Subleading to xy, subleading to x y squared, etc. And all of them are subleading to x squared. So in other words, you first compare the degrees of x, then you compare the degrees of y. And when you have more variables, you first compare the degrees of the first variable, then you compare the degrees of the second variable, and so on, you continue. Now it's an exercise to check that this monomial ordering satisfies all possible conditions there, but that's true. Now, another example would be the so-called total degree lexicographic order. Okay. And here you first compare the total degrees of monomials, and then you compare the degrees of the first, the degrees of the second, the degrees of the third. So again, in f of xy, this means that 1 is subleading to y, subleading to x. So those are of degree monomials of degree 1. Degree 1. Then you take all monomials of the degree 2 and you compare them according to the lexicographic order. So y squared is subleading to xy, is subleading to x squared. Degree equal to 2. And continue. So, okay. So now we can tell. So if we fixed a monomial ordering, once we have fixed a monomial ordering, we can tell which term is leading in multivariable polynomial. So we can construct a division algorithm. So we can construct division algorithm. So we can construct a division algorithm by, well, so we basically start with the polynomial and we always look at the leading term and we make it to cancel. So if we have like two polynomials, f of x and g of x, we look at the leading terms of both of them and we multiply g by a certain factor to cancel the leading term of f of x and continue. So other than monomial ordering, it's really identical to what you will do in the division of polynomials in one variable case. Okay, so now making the story short. In short, one can construct a special generating set. Set for every ideal known as Grobner basis. For every ideal known as Grobner basis. And different monomial orderings correspond to different bases. basis, of course. And kind of then for every polynomial, you can look at the reminders with respect to this Grobner basis, and they will be uniquely determined. So I don't really want to go in the all details. So let's say this allows for canonical generating set for every ideal. So in particular, when we can say when the two ideals are equal to each other, computing this canonical generating set known as the Grobner basis. And they will be equal to each other if and only if this canonical generating sets coincide. So that's, yeah. So let me stop here. And yeah, that's, so during the RR week, I will host office hours according to the usual schedule, and I will post the practice midterm, practice final sometime before the RR week. So now, if you have any questions, please unmute and ask them. Otherwise, I'll just stop recording and continue with office hours.